So if I were to design a neuroprosthetic system using a rat, what I would do is I would simply take the LFP and ECOG and throw out all the oscillations under 10 hertz. I would just bandpass from 10 hertz onwards, and then the rat could potentially use its gamma activity to additionally control a neuroprosthetic device, should it decide to do so. So in the rat, in my task, the sub 10 hertz activity contained redundant information as the spikes, but maybe in the upper greater frequencies than that, there might be non-redundant information in the spikes. Okay, that's the end of the second experiment. I showed that frequencies above 10 hertz in ECOG and LFP may contain additional command information and may be combined with spiking activity for a neuroprosthetics control signal. Okay, I'm talking about my last experiment, and this actually was the experiment I was most excited to do when I joined Daryl's lab. I actually did it in secret for a month and a half before telling Daryl. And Daryl's a good enough advisor that he didn't chastise me for it. All right, so concurrent with the neuromodulation stuff we've done, and I showed you, previous grad student in Daryl's lab, Kevin Otto, was investigating auditory microstimulation as a kind of sensory replacement. I know John thinks that auditory cortex microstimulation is silly. The brainstem does things for a purpose, but Kevin was interested in auditory cortex, and you can see the rat was trained to detect microstimulation of the auditory cortex. If he detected it, he hits the right lever. If he does not detect it, he hits the left lever. This is actual real time of a rat. This is not sped up in any way. See, now it hits the left lever. And so, if you take the pie in the sky neuroprosthetic model of like an Iraqi amputee with a fully functional robotic arm, and the Department of Defense is actually dropping a lot of money into this. It's a $50 million project with the goal of having a robot hand play a piano controlled by brain signals alone. I know John told him at a thesis committee meeting you can throw $50 million at a rock, but that's not going to do anything either. But nonetheless, people are trying. So imagine playing a violin where your motion of your fingers as hands is only generated by your motor cortex. Do you think playing the violin would be easy or hard in that case? What do you need when playing a musical instrument? The feel and the feedback. So you can imagine if we had like a fully functional robotic arm, you would need to receive feedback that you might not even be conscious of. We receive all this feedback from our muscle stretch and joint dynamics. And that is probably going to be required to have a really functional robotic arm playing the piano and the violin. So there's been a lot of effort historically with microstimulation to investigate sensory coding and also as a sensory replacement or augmentation strategy. But if you're going to have motor ensemble activity control a robotic arm, you're also going to need to provide feedback with current technology, intracortical microstimulation, where you stimulate the brain and give the user feedback with the state of its motor cortex. But no one's ever done that. Until today. In this room. I did it. I did it. So why has no one done it? Typical animal training issues. Anyone who does behavior, training animals is hard, painful sometimes. Stimulating chronically and trying to stimulate chronically and record simultaneously decode. So these were rather difficult surgeries, typically taking about 7 or 8 hours, and I would typically bring the rat back to its cage at 2 or 3 in the morning and go home and watch late night TV. So you have a variety of bone screws to anchor all this, some medial forebrain implants, which I'll talk about later, a motor cortex implant in the front of the brain, and we chose to implant the visual cortex as a sensory area in the posterior pole of the brain. And then, there it is, and then it's all sealed up, stitch around here, wait about a week, and begin training the animal. So this is just a variety of variations on a theme. The way this worked is that I would record baseline ensemble this time, not just single units or multi-unit clusters. I would record the baseline ensemble activity. I would then inject current into the visual cortex, and then I would analyze the motor cortex ensemble activity, and if the rat crossed a certain threshold, he would be rewarded. And so this was I think January 30th of last year when I first got it to work, and I felt so good about myself. You can see that the intercortical microstimulation generates a transient artifact on recording hardware, but after this ICMS, the rat increased its neural discharge rate. So this argues it could perceive the visual cortex microstimulation and could appropriately modulate its motor cortex in response. But this is kind of simple. And I remember my thesis committee meeting last August, we were talking about, if you're really interested in feedback, why don't you deliver feedback to the animal during the response sessions? So this is a bit more complicated. Greg, the cameraman there, helped me out with some algorithms. And so we changed the task such that we injected the initial intracortical microstimulation, but then during the response window, for 10 milliseconds out of every 90 milliseconds, we would deliver feedback via intracortical microstimulation to the rat to give the rat some information about the state of its motor cortex ensemble dynamics. We played with a variety of feedback schemes, mostly because, like I said before, I'm an engineer, and engineers like to tinker with things. So I started with an amplitude-based feedback, where for 6 points. Okay, I would vary the amplitude of the feedback pulses as the animal became closer to rewarded. Then I also investigated a rate-based feedback code, where I would increase the rate of pulses as the animal got closer to rewarded. And then when I got some really fancy, expensive new hardware, I moved to a spatial-based code where I would actually vary the site of stimulation to give the animal information about the state of how close it was to being rewarded. What does this look like? I'm going to show you a movie. Now it's kind of complicated, but what you're going to see is on the computer screen a blue line, and once the blue line goes down, that means the motor ensemble has reached the baseline. You'll hear the artifact of the microstimulation and then a bunch of pips, and then you're going to see the blue line start to move as the rat tries to reach the threshold for reward. You're also going to see the rat on the left, and you notice that when it gets the intracortical microstimulation, it immediately turns its head, and that's the behavioral correlate of it detecting it. You could argue that he might just be hearing it, but this is only for the movie. In all other cases, I did not have the auditory monitor on. Whoa. So this is the blue line. It's got to get between these little bands. So you can hear the artifact of the microstimulation. That's the EMG artifact, lots of artifacts. All right, so he's going to hang out there. Yeah, see, he immediately turns his head, tries to reach the threshold bands, and then that's a bunch of weight calculations. Okay, so this was, it's kind of hard to get this to work where all the implants are in the right place. I implanted approximately 12 animals for the study, but really for the feedback, I'm only going to discuss 3. This is a complicated figure. For the first few sessions, he was trained on amplitude, then the rate, and then the spatial. With all 3 schemes, he was able to do the task above chance, though it appeared that he was able to do it best with the spatial task. Whether this is effective learning or the efficacy of the spatial task, I can't determine with this experiment. You have chance in these gray bars. You have catch trials in the gray, and you have the real trials in the black. So to test whether or not the animal was actually using the feedback, we had catch trials where we would play with the feedback to see what the animal was paying attention to. So let's focus in on a session right here. Session 14 consisted of catch trials where, what was it? Where 15% of the trials had no feedback and were unrewarded. And you can see that in the catch trials, there is a transient increase in firing rate with the initial go cue, but it immediately drops down, whereas in the normal trials where feedback's being delivered, you see a persistent increase in discharge rate as the animal attempts to get the task right. So I'm like, oh, cool, the animal's using the feedback. But maybe it's just detecting the feedback. Maybe it's not really being, oh, okay, that was 5 pulses, I must be closer. Oh, I'm at 7 pulses, I'm almost there. We wanted to determine whether or not the animal's actually using the feedback.